Yes, welcome to Transformania. We're going to talk about transformations today. And whereas it was thunderstorming with lightning and thunder this morning, which I thought was going to interrupt the lecture, thus the intro, now it's bright and sunny. Oh well. So, good sign, right? All right, so this is one of the funnest parts of linear algebra. There are transformations between vector spaces. And so for example, here's a transformation. It takes a vector in R2 and turns it into a vector in R1 by multiplying those two components. So that's a transformation or transform from R2 to R1. It goes from R2 to R1. So we draw this kind of thing to represent it. That's a mapping. So T1 is a mapping or a function that takes vectors in here and makes vectors appear over there. Okay, here's another example. Examples are always good when you're learning something. And how's the glare factor? Pretty bad. Let me move this. Does that help? Right, okay. Here's another transformation, T2. Also goes from R2 to R1. Takes a vector xy in R2 and makes a 1-by-1 matrix out of it, also known as vector in R1, by multiplying x by 3 and y by 5 and taking their difference. Okay, so that's a mapping, a function from R2. Take any vector in here and you get a vector in R1. Okay, so those are examples of two transformations. Only one of those transformations, what we're going to call a linear transformation. And linear algebra is really the algebra of linear transformations. But let's get a little bit more specific about what we mean by a transformation. Okay, so to have a transformation between two vector spaces, you need two vector spaces, V and W, but they have to be over the same underlying field, F. Okay, so in those examples, V was R2, W was R1, and the underlying field was just the set of real numbers. A transformation is a function from the vector space V to the vector space W. So we call the vector space V the domain, and the one it's landing into or mapping into is called the codomain, right? That is distinct from the word range, which you might remember from your function days. Range is something else. And in fact, sometimes the range is a vector space, subspace of W. It's the set of all little vectors W in the vector space W, in the codomain, for which there exists a vector in the domain such that T of V is equal to W. Okay, so that word range here does correlate to your definition of range from college algebra, calculus, and so on of a function. Here's a new thing. It's called the kernel. The kernel of a transformation is a subset of V. It's all those vectors in V such that T of V, the transformation of V, maps to the zero vector in W. Why is it called a kernel? Well, probably because of this little graphic. Let's see, where can I put this? We have a little space in here. All these transformations have a tendency to be sketched out. I got this space free? Yeah, okay. So transformations have a tendency to be sketched out by using two pictures. Pictures of the mapping this way. So some transformation goes from one kind of vector space, V, to another vector space, W, okay? And the part of T that gets mapped, the part of V, that gets mapped to the zero vector over here in W. That gets called the kernel. So you see this little darkened bit gets called the kernel. Well, it looks just like a kernel that you find in a nut, right? That part of it, that sort of central part of it. I don't know any botany, but anyway, so that gets called the kernel. Everything that gets mapped to the zero vector underneath the transformation. Okay, so the kernel is a subset of V. The range is over here. It may not necessarily fill up all of W, right? It's a subset, so this is the range over here. Okay. So for example, if I had a transformation, let's say T3, that takes a vector from R2 and maps it to, let's say, x squared, y squared, right? All those entries to those real numbers would be real. So in this case, the range of T3, would just be equal to R plus, meaning all the real numbers except for the negative ones. And that's a subset, not equal to R, right? So that's an example of the range not filling up the whole codomain. All right, so what do we know about transformations? So that's here's an example of a kernel. Excuse me, let's come back over here. I forgot these were already written. So back to this first transformation T1 that takes a vector AB and maps it a 2 by 2 by 1 vector AB and maps it to a 1 by 1 a matrix vector in R1 A times B. Right. What's the kernel for this mapping? The kernel, and can you answer questions like this? The kernel is a subspace of, a subset of what? R to the, right? It's got to be R2. Such that T1, what is the kernel? It's the set of all of those vectors such that T1 of a vector gives you the zero vector in W. What does the zero vector in there look like? Well, it looks like a 1 by 1 matrix with the zero from the field in it. In other words, the real number 0. So, a 1 by 1 matrix with 0 in it. What would map to that? Again, what does the mapping do? What does T1 do? It takes this pair and multiplies them. So all those vectors for which their product is equal to 0 belong in the kernel of this mapping. Well, if x times y is equal to 0, remember the zero factor principle, that tells you that either x is equal to 0 or y is equal to 0. So the kernel looks like this, the x-axis and the y-axis. Set of all vectors that lie along the x-axis or the y-axis. Is that a subspace? You should stop the video and answer that question. True or false? Either give, if you say it's true, give a proof. If you say it's false, give a counterexample. Let's go look over here at the second transformation. Let me erase this guy here. It's kind of in the way. What's going on here with T2? And the other question is, can you see this? Let me see. It's my glare factor here. I'm trying to get you to look there. And we just need to rotate this. There we go. Okay. What's the kernel of T2 look like? Here, remember, here's what T2 looks like. It looks like 3. You take an xy vector with two components x, y, and 3 times x minus 5 times y. You'll notice that's a linear combination of the components. Anyway, that goes from R2 to R1. What's its kernel? All right, so whenever you're asked what a set is, just go to the definition. Okay, it's got to be the set of all vectors in the domain such that if you take their components and put them through that operation and stick that into a 1-by-1 matrix, if this vector belongs to the kernel, then this number has to be, this 1-by-1 matrix has to be the 0 vector for W, which is, we could write it this way. It's the 1-by-1 that's equal to this 1-by-1. But that's another way of saying 3x minus 5y is equal to 0. Or it implies it, right? And so if that's the case, what have we got? Minus 5y is equal to negative 3x, or y is equal to 3/5 x. So that's what the property I put in here. You didn't see this? Okay. So what does that look like? What does the kernel of T2 look like in the vectors in the domain space V, which is R2? Well, it looks like the line L1. If L1 is all the vectors that are parallel to this line, right? So it includes the 0 vector, a whole bunch of these vectors. In fact, all these could be thought to be the span of just one vector. Is the kernel of T2 a subspace of R2? You should stop the video and prove that, or disprove it. So these two types of transformations, T1 and T2, are not just pretty transformations, they're also showing up a difference between types of transformations. Only one of them is a linear transformation. Okay, so we need a definition of what a linear transformation is. And that puts us back over here. All right, so a linear transformation, on the other side, look at the shadows, right? So a linear transformation is a transformation from a domain space, which is a vector space, to a codomain vector space, where those two vector spaces have to share the same underlying field, and it satisfies this property, that for all vectors v1 and v2 in the domain, and for all alpha and beta in the field, T of, that's supposed to be T of their linear combination, alpha v1 plus beta v2. So for an arbitrary linear combination in the domain space, if you take a linear transformation of it, you get the same thing as that linear combination of its images. We say that T of v1 is the image of v1. T of v2 is the image of v2. It's some vocabulary. In other words, it's a linear transformation if it acts nicely with linear combinations. Remember, linear combination is one of those words whose definition you need to have down solid, okay, because we're going to use it a lot. I'd like to point out that this definition of a linear transformation, when I say for arbitrary vectors in the domain space and arbitrary scalars in the field, that arbitrariness includes when the alpha and the beta are equal to the 0 in the field. So if you plug those into here, if you put in 0 scalar here or 0 scalar there, you've got 0 vector plus 0 vector. By which axiom was that? Or which problem that we worked in 4.1? You'll have 0 vector plus 0 vector. In other words, 0 vector, here you'll be taking T of the 0 vector. Well, if it's a linear transformation, that same 0 and 0 here have to be on the other side of the equation. So that's 0 scalar times some vector in W plus 0 scalar times some vector in W. That's another zero vector in W. That's a zero vector in W. So this statement includes the one that your book kind of points out separately, that if it's a linear transformation, it has to be true that T of the zero vector in the one space has to be equal to the zero vector in the other space. That's a nice property to know when you're trying to pick off some transformation for not being linear. There's a lot of examples of transformations that fail that, and if you just have that, it's an easy way of saying, okay, well, that's not a linear transformation because it didn't map the zero of the domain space to the zero of the codomain space. Okay. For the next bit, where I'm going to talk about this theorem, pretty important theorem in the linear algebra class, and that is for any transformation that can be described, or we say represented by, a matrix multiplying on the left of the vector. Okay? So it turns out that there are many transformations that are described this way. What is the transformation going to do to the vector? It's going to multiply it by a matrix on the left. Appropriate dimensions, of course. Okay. If that's the case, if the transformation can be represented by A, we will write T is equal to T sub A for that particular matrix, meaning that matrix. And if, so if A is M by N here, times an N by 1 vector here, will give us an M by 1 vector. Just add that in there. A little calculation takes place a lot. So this guy is M by N, and this one is N by 1. Then the product of those two is something that is an M by 1 matrix, right? Okay. And so it's a vector in Rm. Any transformation that you can represent in that way is definitely going to be a linear transformation. Now, why is that? First of all, let's remember some other key facts about matrix multiplication. Okay. Your book in section 1.4, page 39, calls this theorem 5. I don't know if we need to call it that, but okay. It's some key matrix multiplication properties. That if you have a matrix times a sum of two vectors, okay, matrix multiplication, everybody's a matrix. This is something in Rn. So if you have an Rn vector added to an Rn vector, which could be written as an n by 1 column matrix added to an n by 1 column matrix, that makes an n by 1 column matrix. And you can multiply it by an m by n matrix, right? But moreover, not only can you do it, it satisfies this distribution. But that is going to be the same thing as if you had done them singly, ax plus ay. What is that? So an example of this first one, just to get you started, would be, let's let A be the matrix 1, 2, 3, 4, x be 5, 6, y equal to 7, 8. So the left-hand side of this equation here, an example of it is right there, okay? But from matrix addition, you add those two, you get 12, 14 inside there. If you multiply a 2 by 2 by a 2 by 1, you get a 2 by 1. It's going to be equal to 40, 92, okay? So the left-hand side here is equal to the 2 by 1 vector 40, 92. On the other side, on the right-hand side of the equation, ax plus ay, what does that look like in this example? So this is a good trick to just, when you're looking at a theorem, you're trying to understand it, give yourself some example to work with. It helps you understand it better, I think. So 1, 2, 3, 4 multiplied by 5, 6 gets added to 1, 2, 3, 4 and multiplied by 7, 8. That's what the right-hand side is representing. That gives you, this one becomes 5 plus 12, or 739, and this one becomes 2353. You add those two together, oh look, it's the same 4092. So the left-hand side is equal to the right-hand side. That's not a proof, but it helps you understand what the heck this statement is saying. Do the same thing for this one. Stop the video and make your own example of that one. This is a good study tool. When you're looking at some theorem that you're supposed to be understanding or some properties that you need to use, and it's just all kind of looking like a bunch of Greek or Latin letters, come up with some examples and just put those examples in, see what happens. It often helps you understand much better what's going on. Well, anyway, so using these matrix multiplication properties that you've had forever, supposedly in your 13, 14, you were taught that. But they certainly didn't phrase it that way. Anyway, using that, we're going to have this theorem. We're going to be able to prove this theorem, sorry. You've already seen it. Let's prove it. Any transformation that can be represented by matrix multiplication is a linear transformation. That's the statement. Proof, one line. T sub A of alpha V1 plus beta V2, where alpha and beta have been chosen arbitrarily, V1 and V2 are arbitrary vectors in Rn, right? If T sub A can be represented by multiplying that vector, that one vector on the left by A, then by that first matrix multiplication property, that's the same thing as A times alpha V1 plus A times beta V2. Okay, that's using that property that I worked out on the side board, right? By the second property that you worked out, these scalars can come out front. Okay, because this is all matrix multiplication. Well, look at that. T sub A of a linear combination is equal to the same linear combination, same scalars of their images. That's a definition of linear transformation. So, and we've shown, sorry, this is a QED moment, right? We're done right here. We just showed that if a transformation can be represented as matrix multiplication transformation, it's definitely a linear transformation. We're done with that statement. Now, which of those transforms above were linear? T1, T2. Which ones were linear? You should stop the video, work with T1. It looks like this. Excuse me. Oh, my goodness. T1 to find there, right? The one that takes X, Y, 2 by 1 matrix and sets it to 1 by 1, taking the product of those components. Is that a linear transformation? See if this helps you understand what's the property of being a linear transformation by taking an example and seeing if it satisfies the properties. Stop the video, check that out. We've come back. Now do the same thing for T2. This linear transformation takes a 2 by 1 and maps it to a 1 by 1, where the components x, y got put into a linear combination 3x minus 5y. Is that a linear transformation? Well, if you could just show that this could be represented, so sorry, stop the video, you do it yourself, but when you come back. Right, okay, you could use this theorem if you can show that this transformation can be written as using matrix multiplication. And it looks pretty linear, doesn't it? That's the same thing as multiplying xy on the left by what matrix? You stop the video and fill that in. If you start the video again, it looks like I gave you the wrong size, right? So we have to go from a 2 by 1, right? 2 by 1 has to get multiplied by something to become a 1 by 1. What is the size of this? Shouldn't be, I misled you. Shouldn't be 2 by 2, should it? It should be 1 by 2. There, right? 1 by 2 multiplied by 2 by 1 should just give you a 1 by 1. What should be in here? Stop the video, you figure it out. This multiplied by that has to be added to this multiplied by that, so that should be a 3, and that should be a minus 5. That will give us our 3x minus 5y. So, notice that we have a transformation T2 is going from R2 to R1 by using a 1 by 2 matrix. And since we can rewrite it that way, it is a linear transformation. So this guy is linear by theorem 1. And I'm assuming you found out that T1 was nonlinear by coming up with a counterexample to the properties of linearity.